In the name of Almighty God, I'm Master Sankashi, and today I want to talk about plasma alpha to gamma transition. Large volume and uniform atmospheric glue discharge are finding a vast range of processing applications, many of which have been traditionally addressed with the vacuum plasma technology. When excited at kilohertz or above, these atmospheric plasma operate typically at low current densities below 30 milliampere per square meter, and often they are perceived to have very similar properties regardless of their operation conditions. Recently, a radio frequency atmospheric glue discharge was observed at high current density of up to 1 ampere per square centimeter, thus suggesting a previously overlooked and potentially different operation regime. Through a computational study of radio frequency atmospheric glue discharge over a wide range of current density, this paper presents evidence of at least two glue modes, namely the alpha mode and the gamma mode. It is shown that gas ionization in the alpha mode is volumetric, occurring throughout the electrode gap, whereas in the gamma mode it is dominated by localized events near the boundary between the sheath and the plasma bulk. Secondary electron emission strongly influences gas ionization in the gamma mode, yet matter little in the alpha mode. These findings suggest a wider operation range of atmospheric glue plasmas than previously believed. The constructing dynamic behavior of the two glue modes highlight both the potential to preferentially match the operation regime of atmospheric glue discharge to the specific requirement of their intended applications, and the importance to develop diagnostic strategies appropriate for their operation regime. Atmospheric pressure glue discharge, or APGD, have recently commanded much attention, fueled by their promise to rival the widely used low pressure glue discharge and their facilitation of numerous applications through the removal of the usually indispensable vacuum chamber. There are capacitive non-thermal plasmas generated between two parallel electrodes that are either metallic or coated with a dielectric layer, and their generation has been achieved over a very wide spectrum from DC to kilohertz and megahertz to microwave. They can also be generated as surface wave discharge. Today, APGD are finding wide-ranging application including etching, deposition, surface modification, and sterilization. The progress of their fundamental understanding, on the other hand, lags markedly behind their technological advancement, largely due to comparatively few theoretical studies so far. One common perception is that atmospheric pressure glue discharge may possess similar properties regardless of their operation conditions. Yet it is known that glue discharge at low and medium pressures have different operation modes of contrasting behaviors in, for example, their ionization mechanism and current voltage characteristics. If glue discharge at atmospheric pressure are also found to possess distinctively different operation modes, there will be important implications to their future development strategies, not least of which is the possibility to preferentially match the operation regime of APGDE, which is atmospheric pressure glue discharge, to the specific requirements of their intended applications. Therefore, it is important to establish whether different glue modes exist in atmospheric discharge. In this simulation, we aim to substantiate the experience different atmospheric plasma glue discharge modes through a study of their dynamics and ionization mechanism. Our work is based on the radiofrequency atmospheric plasma glow discharge, for which studies have been reported of their current voltage characteristics, optimal emission, and reaction chemistry. Most experimental and computational studies reported so far suggest that radiofrequency atmospheric plasma glue discharge may operate only in a regime of low current density, typically below 30 milliampere per square meter per square centimeter, and a significant increase in current density tends to evolve the discharge directly into an arc plasma, thus bypassing the gamma mode of larger current density commonly seen medium pressure glow discharge. Recently, this view has been challenged by our experimental observation of a stable radiofrequency glow mode in atmospheric helium at large current density of up to 1 ampere per square centimeter, thus suggesting a possible existence of both the alpha and gamma modes in atmospheric pressure glow discharge. To explore this observation further, with an unambiguous interpretation, a theoretical study is preferred since it allows for access to information on dynamic evolution of many key physical quantities, such as electric field densities of plasma species and electron production rates, that are at present either difficult or expensive to access experimentally. As a result, we have developed a fluid model of radiofrequency atmospheric plasma glue discharge and employed it to study their ionization mechanism over a wide range of current density from 5 to 100 milliampere per square centimeter. It is shown that both the alpha and gamma modes indeed exist in atmospheric pressure glue discharge, and that gas ionization in the alpha mode is volumetric, occurring throughout the plasma, whereas in the gamma mode it is dominated by localized events near the boundary between the sheath and the plasma bulk. It is further demonstrated that plasma chemistry doesn't affect the presence of the two glue modes, but strongly influences their transition voltage from the alpha mode to the gamma mode. Computational model. As a test vehicle to demonstrate the existence of different glow modes in atmospheric plasmas, we consider radiofrequency glow discharge in atmospheric helium, given that impurity gases such as nitrogen are known to be important in helium atmospheric plasma glow discharge. We consider both a pure helium atmospheric plasma glow discharge mode and a helium and nitrogen atmospheric plasma glow discharge model so as to construct out the general characteristics of possible atmospheric plasma glue discharge modes. Our pure helium plasma model considers six species, namely electron, helium ions, helium positive, excited helium atoms, helium star, dimmer helium ions or helium 2 positive, excited dimmer helium or helium 2 star, and background helium atoms, which is uh, helium alone. Similar to a comparable numerical study of the radiofrequency atmospheric plasma glow discharge, our model includes nine chemical reactions among these plasma species, including direct ionization, excitation, de-excitation, charge transfer from atomic helium ions to dimmer helium ions, the stepwise ionization to helium star, and recombination rates for all other reactions are identical to those used in this simulation. Our plasma model is a self-consistent and continuum model. Its governing equations consist of the mass conservation equations to determine the densities of each plasma species, the current continuity equation for calculation of the electric field, and the electron energy conservation equation for the electron mean energy. Specifically, they are given as the partial differentiation of the number of electrons to the time is equal to minus the partial differentiation of tau electron to the displacement plus Kig epsilon ning, where n and tau are the density and flux of a species, epsilon the electron mean energy, and J the current density, and Kij and Lij are respectively the reaction rate and the energy gain lose rate due to the reaction between the species I and J. Chi is the momentum transfer frequency corresponding to the elastic collision between electrons and background gas atoms. D is the diffusion coefficient. Micro is the mobility, and E is the electric field. M is the mass of plasma species, and T is the temperature of plasma species. Subscripts E plus star and neut denote respectively electrons, ions, metastables, and neutral particles. P presents different ions considered in the model. Fluxes of all plasma species are given by tau is equal to minus dE epsilon, and the partial differentiation of the number of electrons to the displacement minus microelectron, n electron, and E. Transport properties are the same as those used in literature. The ionization coefficient is calculated as a function of the electron mean energy rather than the local electric field. Our model is one-dimensional with the governing equation solved in the direction perpendicular to the electrode plane. We assume that the gas temperature is 393 Kelvin and externally applied radio frequency current is of sinusoidal waveform at 13.56 MHz. The boundary conditions for electrons at the surface of both electrodes are tau e is equal to minus gamma sigma p tau plus p, where gamma is the secondary emission coefficient for neutral particles, positive ions, and metastable. The flux at the electrodes is dominated by drift, and the diffusive flux is negligible. To include impurity nitrogen, we have also developed a helium nitrogen 2 plasma model by adding nitrogen molecules, nitrogen atoms, atomic nitrogen ions, and dimer nitrogen ions, and to the six plasma species in the pure helium plasma model. As a result, we have five nitrogen only reactions, including electron impact dissociation of nitrogen molecules, electron impact ionization of nitrogen atoms and molecules, recombination of nitrogen ions, and six nitrogen helium coupling reactions, including panning ionization of nitrogen molecules by helium metastable and charge transfers from helium ions to nitrogen ions. These additional reactions and rates are identical to those used in the simulation, which their inclusion via Kij and Kij, the governing equations of the helium-nitrogen plasma model, are also given in the next equation. For validation of our plasma models, we consider a 13.56 MHz atmospheric plasma glow discharge in a 600 Tor helium nitrogen mixture, which the electrode gap at 2.4 mm and the secondary electron emission coefficient at 0.03. The choice of these parameters is to compare our simulated current voltage relationship with the available experimental and numerical data obtained under the same operation conditions. The nitrogen content is set at 0.16 ppm in our simulation. This is within the range of impurity nitrogen that can be realistically expected for the comparison experiment. Though it is less than 5 ppm used in the numerical study, as shown in the simulation, the agreement is in generally very favorable and particularly so with the experimental results, suggesting that our plasma model is capable of accurately capturing the main features of radiofrequency atmospheric plasma glow discharge and as such is reliable for the study of their operation modes. Further simulation with a smaller secondary electron emission coefficient at 0.01 leads to an almost identical current voltage relationship to this simulation. With an emission coefficient of 0.03, thus suggesting the insignificance of secondary electrons in this case. Different atmospheric plasma glow discharge modes and their mechanism. Evidence of different atmospheric plasma glow discharge operation regimes. We consider possible operation regimes in pure helium atmospheric plasma glow discharge using our pure helium plasma model, and here in this simulation shows the variation of maximum electron density as a function of the radio frequency voltage amplitude for an atmospheric helium discharge generated at 30.56 MHz and with a secondary electron emission coefficient of 0.1 when the radio frequency voltage amplitude is less than 410 volts. The electron density increases approximately linear with the radio frequency voltage at a rate of 1 multiplied by 10 to the power of 9 centimeter to the power of minus 3 per volt. As the radio frequency voltage amplitude becomes greater than 410 volts, the electron density increases much more significantly. In other words, the radio frequency voltage amplitude at 410 volt appears to be a transition point that divides two distinctly different APGD regimes. Significantly, the distinct change in the voltage dependence of the electron density resembles that of the glue discharge at medium pressures, suggesting the existence of two different APGD modes similar to the medium pressure glue discharge. The regime of gradual density change below 410 volt in the simulation is the alpha mode, and that of rapid density change above 410 volt is the gamma mode. It is also interesting to note that the last data point of this simulation at 4.2 multiplied by 10 to the power of 11, which is in the gamma mode and has a smaller radio frequency voltage of 406 volts than 410 volt of the alpha gamma mode transition point at 3.6 multiplied by 10 to the power of 11. This voltage decrease is very similar to the voltage drop accompanying the alpha gamma transition in medium pressure glue discharge. Ionization mechanism. To understand the different behaviors of these two glue modes, we consider their ionization and calculate their electron production rate. In this simulation, we plot the dynamic evolution of the normalized electron production rate across the electrode gap when the current density amplitude is 10 milliampere per square meter. This case is representative of the alpha mode and corresponds to the first point where the maximum electron density is 4.6 multiplied by 10 to the power of 10 and the radio frequency voltage amplitude is 217 volt. The dashed curve indicates the boundary between the schist and the plasma bulk, estimated using a technique reported recently. It is evident that significant electron production occurs both between the schist region, for example, between the schist boundary and its nearest electron, and the plasma bulk region. So gas ionization is volumetric and very similar to the alpha mode of glue discharge in medium pressures. As an example of the gamma mode, plots the evolution of the normalized electron production rate across the electrode gap when the peak current density is 70 milliampere per square centimeter. This corresponds to the last point in the figure here, for which the maximum electron density is 4.2 multiplied by 10 to the power of 11. It is clear that electron production is largely confined in the boundary area between the sheath and the plasma bulk, and intriguingly, this is very similar to the behavior of medium pressure glow discharge in the gamma mode. To provide further insight into electron production, we plot here in this simulation the spatial profile of the electron mean energy at the instant of the largest electric field in sheaves for the two cases. It is seen that for the case of J is equal to 10 milliampere per square centimeter in the alpha mode, the electron mean energy changes modestly across the electrode gap with a peak of 4.7 electron volt in the sheath and at least 1.9 electron volt in the plasma bulk region. Compared to the helium ionization energy of 24.6 electron volt, the small electron mean energy in the sheath suggests that many electrons in the sheath region have a kinetic energy below 24.6 electron volt, and their acceleration needs to be continued into the plasma bulk for their kinetic energy to reach 4 24.6 electron volt. This is essentially why electron production here is volumetric. Both the volumetric electron production and the small electron mean energy in the sheath are charged and characteristics of alpha mode. It is worth mentioning that the gradual voltage dependence of the electron density in the alpha mode is likely to lead to comparatively easy control of plasma stability, and this is partly why most reported experiments of the radio-frequency atmospheric plasma glow discharge were operated in this mode. For the 70 milliampere per square centimeter case in the gamma mode region, the maximum electron mean energy is seen to be at 10.3 electron volt, much greater than 4.7 electron volt in the alpha mode case of this simulation. Therefore, compared to the alpha mode case, significantly more electrons can now reach the helium ionization energy within the sheath, thus resulting in most ionization events being confined to the sheath bulk boundary region, as indicated here in this simulation. The more frequent ionization events in the sheath suggest a more rapid energy loss among more energetic electrons, leading to a smaller electron mean energy of 0.7 electron volt in the plasma bulk compared to 1.9 electron volt in the 10 milliampere per square centimeter case. These observations are consistent to behaviors of medium pressure glue discharge in the gamma mode, and as such offers further evidence of the existence of the gamma mode in the atmospheric plasma glue discharge. An important point to note is the rapid electron density increase of the gamma mode in this simulation, which in practice relates to similarly rapid increase of power dissipation in the plasma. Without restriction, this sharp power increase can cause considerable gas heating and thus rapidly evolve the glue discharge into the arc plasma. This is partly why the gamma mode is difficult to be observed in some radiofrequency atmospheric plasma glue discharge experiments. On the other hand, if the current density is appropriately restricted by means of resistive elements in the discharge circuitry, for example, radiofrequency atmospheric plasma glue discharge can be safely operated in their gamma mode without undue gas heating, thus expanding their operation range beyond previously believed. An ability to restrict the discharge current is important not only for the control of glue to arc transition but also for achieving the highest possible plasma density that are often beneficial for applications. This simulation shows clearly that larger electron density is achieved in the gamma mode, given that reactive plasma species tend to be more abundant at large electron density. A controlled operation of atmospheric plasma glue discharge in their gamma mode is desirable, especially for applications in which processing efficiency is important. Effects of secondary electrons chapter. To further support the hypothesis that the operational regime above 410 volt in the simulation is in the gamma mode, we plus the voltage dependence of the electron density for different secondary electron emission coefficients in the simulation. With a large secondary emission coefficient, more electrons are available to be accelerated to the helium ionization energy within the sheaths, thus resulting in a large space charge field to be established at a relatively low radio frequency voltage. Again, this is very similar to that in medium pressure glue discharge and responsible for an early onset of the gamma mode in the simulation when the secondary emission coefficient is zero point 0.3. Also, when the current density is sufficiently small, for example, less than 30 milliampere per square centimeter, that corresponding to a radio frequency voltage of about 300 volts. Secondary electron emission doesn't significantly influence the electron density and indeed other electrical characteristics. So the ionization by secondary electron emitted from the electrodes is not important in the alpha mode and instead primarily electrons accelerated by the oscillating field of the applied voltage dominated and the ionization. This also contributes to the volumetric nature of gas ionization in the alpha mode. In other words, effects of secondary electrons are insignificant where the frequency atmospheric plasma glow discharge operates with low current density and in the alpha mode. The chapter of effects of reaction chemistry to establish whether the presence of the two atmospheric plasma glow discharge mode is generic. We use our helium nitrogen plasma model to study a 13.56 MHz atmospheric plasma glue discharge in a helium nitrogen mixture with a nitrogen content at 0.60 ppm. Again, the electron gap is 2.4 millimeter and the secondary emission coefficient is 0.5, and the simulation shows the maximum electron density as a function of the peak radio frequency voltage, and the division between the alpha mode and the gamma mode is distinct at a radio frequency voltage amplitude of 284 volt. Further, numerical simulation is then used to study the regions of the most significant electron production and the effects of the secondary electron emission, and its results resemble in here in the simulation and respectively, thus confirming the existence of both atmospheric plasma glow discharge modes. The early onset of the gamma mode at a smaller radio frequency voltage in the helium nitrogen radio frequency atmospheric plasma glow discharge is related to the fact that its gas ionization is considerably enhanced by the panning ionization of nitrogen by helium metastables. Therefore, even at a modest radio frequency voltage, adequate electron production is achieved in the schist set up a significant space charge field there for the transition from the alpha mode to the gamma mode. From the standpoint of electron production, the more significant gas ionization in the helium nitrogen plasma is equivalent to a larger secondary emission coefficient in the pure helium atmospheric plasma glue discharge of this here simulation. In summary, plasma chemistry doesn't affect the presence of the two glow modes but influences strongly the transition voltage from the alpha mode to the gamma mode. For both diagnostics and applications of atmospheric plasma glue discharge, larger electron density of the gamma mode is desirable since this usually leads to more abundant reactive species. Here, the simulation shows the time average spatial profile of helium ions and metastable. It is seen that as the APGD operation evolves from the alpha mode to the gamma mode, densities of all the plasma species increase. Intriguingly, atomic species increase much more significantly than molecular species, and here in this simulation shows the maximum densities of helium ions, nitrogen ions, and helium metastables at the two current densities. It is clear that in the alpha mode, the molecular species are more abundant by at least one order of magnitude than their atomic counterparts. So, if APGD operates in the alpha mode, it is advantageous to base both plasma diagnostics and application strategies on molecular species. In the gamma mode, on the other hand, atomic and molecular species are similarly abundant, and so it is important to consider both when developing their diagnostic methodologies and their applications. In general, the contrasting features of two modes offer the potential to preferentially match the operation regime of atmospheric plasma glue discharge the specific requirements of their applications and underline the importance to develop diagnostics strategies appropriate for their operation regime. And the chapter of conclusion, a self-consistent computational study is presented to substantiate the existence of both the alpha mode and the gamma mode in radio frequency APGD and to unravel their ionization mechanism. It is established that gas ionization in the gamma mode is localized, whereas that in the alpha mode is volumetric. Secondary electron emission strongly affects gas ionization in the gamma mode, but matters little in the alpha mode. It is also known that if the current density is restricted, appropriate radio frequency APGD can be operated in the gamma mode safely without the danger of evolving into arc plasma. This finding suggests a wide operation range of radio frequency APGD than previously believed. Furthermore, the distinctively different dynamic behaviors of the two glue modes both offer the potential to preferentially match the operation regime of atmospheric plasma glue discharge to the specific requirements of their intended applications and emphasize the importance to develop diagnostics strategies appropriate for their operation regime. And here I want to make a review for our one-dimensional simulation. You see that the geometry I have selected is just one line, and here you see the frequency I have selected is 13.56 megahertz, and uh, potential a power reference is 1 watt. And the physics that I have used, physical module is plasma time periodicity, and you see the different species here and the plasma model. The temperature is 300 Kelvin and the atmosphere is pressure is 1 atmosphere. The equations as I have described is the differentiation between number of electron to the ton plus delta tau E is equal to Re minus U delta N E. The species that are here is about the electron. The species name is argon, but I described the element of helium. But here in this species that I have selected is argons, and you see the electron impact reaction, the formula of electron impact reaction. Then there are three different studies, time periodic, and you can see the power and the number of electrons applied to voltage. You see the voltage amplitude at the horizontal axis, which is between 150 volts to 350 volts, and the power terminals based on watt in the vertical axis from 50 to 700. And you see the bending here. Also in the right axis we have a average number of electrons based on length to the cubic meter. You see the electron density alpha regime, temperature, power absorbed by alpha regime, and electron source here. Thank you so much for watching my tutorial video until the end. And you can also download this simulation from github.com/mahsasgiri, and you can search it by type plasma underline capsule underline alpha to gamma transition. Today is the 9th of February in 2026, and the time is 2:57 p.m. o'clock.